This footpath bridge was chosen by Sri out of the 3 structures I sent to Sri as candidates for my video project analysis. I decided to analyze it as I walked over this tiny bridge most days during my exam preparation. The bridge is 6 meters in length and 5.52 meters wide. As a requirement for VP Task 2, we were required to break the structure into 2 different beams with different lengths and loads. Beam A is 4.75 meters in length, while beam B is 3.62 meters long. Our first task was to calculate and graph the shear force diagrams and bending moment diagrams for each beam. Beam A had a point load that was equivalent to the last number of our student IDs multiplied by 1.33. Hence, I had a point load of 7.98 kilonewtons at the center of the beam. I first calculated the reaction forces, then the internal forces to find the shear force and bending moment functions. To calculate the internal forces, I cut the beam into 2 segments, one just before the point load, which was x1 meters long, this was segment AC, and another just after the point load, which was x2 meters long, this was segment CB. These functions calculated the max shear force, which was 3.99 kilonewtons at the start of the beam and 9.47 kilonewton meters for bending moment, which was at the very center of the beam. Beam B had a uniform distributed load, or UDL, of 7.98 kilonewtons per meter across the whole beam. I converted that UDL into a point load of 28.89 kilonewtons in the center of the beam to calculate the reaction forces. I then cut the beam x meters long to find the V and M functions in order to graph the diagrams. The max shear force was calculated to be 14.445 kilonewtons at the start and end of the beam, whilst the max bending moment was at the center again with 13.07 kilonewton meters. We had to choose the beam with the largest shear force and bending moment for VP Task 3, hence why I chose beam B to analyze. All my calculations were all converted to newtons and meters to make sure things were less complicated. I sketched the cross-section of the beam with the neutral axis halfway through horizontally at 0.1 meters. To calculate the max bending stress, I used the max bending moment calculated from VP Task 2, which was 13,070 Newton meters, the distance between the max bending stress and neutral axis, which was 0.1 meters, and the moment of inertia of the cross-section. The calculated max bending moment came to 0.87133 megapascals. To calculate the max shear stress, I used the max shear force calculated from VP Task 2, which was 14,445 newtons, area between the max shear stress and neutral axis, the distance between the centroid of the area and neutral axis, and the width of the cross-section, as well as the moment of inertia of the cross-section, which all came to a max shear stress of 0.048150 megapascals. To calculate the maximum principal stresses, I used the initial condition of the bending stress in the x-plane, which was calculated to be 0.87133 megapascals, bending stress in the y-plane and the shear stress in the x and y plane to be 0. Hence, the maximum principal stress was 0.87133 megapascals and 0 megapascals. The same initial conditions were used to find the failure planes of the stresses, which came to 0 and 90 degrees. To calculate the maximum in-shear stresses, I used the initial condition of the maximum shear stress in the x and y plane, which was calculated to be 0.04815 megapascals, bending stress in the y plane and bending stress in the x plane to be 0. Hence, the maximum in-shear stresses were positive and negative 0.0481500 megapascals. The same initial conditions were used to find the failure planes of the stresses, which came to 0 and 90 degrees. The maximum slope functions were calculated by integrating the maximum bending moment function and the initial condition of the slope equaling to 0 at the midpoint of the beam to find the value of the constant. This function was then divided by the Young's modulus of concrete, which is 60 gigapascals, and the moment of inertia of the cross-section, with x being 0, as this is when the slope is maximum. The maximum slope came to 0.01 degrees. The maximum deflection function was calculated by integrating the maximum slope function, the initial condition of deflection equaling to 0 when x is 0, to find the value of the constant. The function was then divided by the Young's modulus of concrete, which is 60 gigapascals, and the moment of inertia of the cross-section, with x being 1.81 meters, which is the midpoint of the beam, as this is when slope is maximum. The maximum deflection came to 1.98 times 10 to the negative 4 meters long.